Greetings. Today we will delve into the fascinating topic of modern computing technologies, namely, what are quantum-centric supercomputers? This concept represents a revolutionary step in the development of computer science, combining principles of quantum mechanics with the power of classical high-performance systems. I will explain this in detail, step by step, so that you can fully understand the essence, advantages, and prospects of this technology. We will base our discussion on the most current data as of September 2025, taking into account the latest achievements of leading companies such as IBM and AMD. First, let's define the key terms. A quantum computer is a computing system that uses quantum bits or qubits instead of classical bits. Unlike traditional computers where bits can only be 0 or 1, qubits can exist in a state of superposition, meaning they can be both 0 and 1 simultaneously, as well as in a state of entanglement, which allows for parallel computations at an exponential speed for certain tasks. Classical supercomputers, such as those based on CPU and GPU processors, are powerful for processing large volumes of data, but they are limited in solving problems that require modeling quantum systems, for example, simulating molecular interactions or optimizing complex algorithms. A quantum-centric supercomputer is a hybrid architecture where a quantum processor is integrated with classical computing resources, forming a unified system optimized for collaborative work. In such a system, the quantum computer handles tasks that are quantum in nature, such as simulating the behavior of atoms and molecules, while classical supercomputers process large arrays of data, coordinate processes, and execute artificial intelligence algorithms. This integration enables the achievement of so-called quantum advantage, a state where a quantum system solves problems faster or more accurately than any classical computer, even the most powerful one. How exactly does such a system work? Imagine an orchestra where the quantum processor is the soloist and the classical nodes are the accompanying ensemble. The architecture involves parallel and asynchronous execution of hybrid tasks. The quantum computer processes quantum algorithms such as Shor's algorithm for factorization or Grover's algorithm for search, while classical resources provide data pre-processing, error correction, and post-processing of results. For example, in chemistry research, the quantum processor can model the electronic structures of molecules, while the classical supercomputer optimizes model parameters using machine learning. This synergy requires specialized software for orchestration, such as IBM's Qiskit, which allows developers to create hybrid programs that seamlessly transition between quantum and classical components. One of the key advantages of quantum-centric supercomputers is their ability to solve problems inaccessible to classical systems. In physics, for instance, they can simulate quantum phenomena in materials, accelerating the development of new superconductors or batteries. In chemistry, they model reactions at the molecular level, aiding in the creation of new drugs or catalysts without costly experiments. In artificial intelligence, such architecture integrates with AI to optimize neural networks, where the quantum component accelerates training on large datasets. Moreover, these systems help address global challenges such as modeling climate change, optimizing logistics, or cryptography, where classical methods encounter computational barriers. Let's consider real-world implementation examples. IBM is a pioneer in this field. In 2024, they introduced the concept of a quantum-centric supercomputer, and by 2025, they implemented prototypes using processors with over 100 qubits. In August 2025, IBM announced a collaboration with AMD to develop architectures where the quantum computer is combined with powerful classical AMD chips, enabling scaling of systems for industrial use. This collaboration aims to create infrastructure where the quantum computer is integrated into data centers, providing access via the cloud. Another example is research on the Archive platform, where scientists demonstrate how such a system solves chemical problems beyond the reach of precise classical solutions using distributed computing. However, not everything is straightforward. Quantum systems still face challenges such as decoherence, the loss of quantum state due to interaction with the environment, and computing errors, which require complex correction methods. Therefore, quantum-centric supercomputers rely on classical resources for stabilization. Additionally, unlocking full potential requires global collaboration. In 2025, the World Economic Forum emphasized the need for partnerships between companies, governments, and researchers to advance this technology. Regarding prospects, the future of quantum-centric supercomputers looks promising. By 2030, systems with thousands of stable qubits are expected to emerge, enabling commercial applications in sectors such as pharmaceuticals, energy, and finance. This technology could radically change the world, accelerating scientific discoveries and innovations. However, it is important to consider ethical aspects such as technology accessibility and its impact on cybersecurity, as quantum computing could break modern ciphers. In conclusion, quantum-centric supercomputers are not just an evolution, but a new paradigm in computing where quantum and classical worlds merge to overcome the boundaries of the possible. Dear viewers, thank you for joining us today. We hope you found this interesting and learned something new. If you enjoyed the video, don't forget to give it a like, subscribe to the channel, and hit the notification bell so you don't miss new episodes. Leave your thoughts and questions in the comments. Your opinion is important to us. See you in the next video.